Welcome back to an introduction to Earth Science. I'm your professor, Dave Cocchiarella. We are working from the textbook Foundations of Earth Science, the 8th edition, written by Lutgens and Tarbuck and brought to you by Pearson Education. Chapter 11 now, transitioning from the ocean to the atmosphere and the heating of the atmosphere. We're going to talk about the composition of the atmosphere, the vertical structure of the atmosphere, the Earth-Sun relationship, and how we heat the atmosphere. And then finally, just a little bit of a conversation about the climate of the atmosphere. So we're going to talk a lot about what's happening with weather and climate processes here in Chapter 11 of Foundations of Earth Science. We start this section of the textbook on weather and climate and atmospheric processes with a focus on the atmosphere, starting with the concept of weather versus climate. Weather occurs over a very short period of time. The weather is what's happening right now. And as you know, the weather is constantly changing, where climate is something that is averaged over a long period of time. And it's a generalized composite of the weather of a region. And when we talk about a long period of time, most climatologists begin with looking at 30-year periods. So what are the averages during that 30-year period? What are the extremes during that 30-year period? And all of that goes into creating what is the climate. Now, the elements of weather and climate are the same thing. It's just looked at over different time scales, one very short and one very long. And of course, those elements are going to be your air temperature, humidity, your type of cloudiness that may be occurring at the time, type and amount of precipitation, air pressure, which is going to be very important. Air pressure ultimately creates the wind, and therefore the wind speed and direction. So the composition of the atmosphere. The air is a mixture. It's a solution, in fact. The air is a lot of different gases that are all mixed together. Air is a mixture of discrete gases. Discrete is simply a word that means alone by themselves. The gas itself creates the whole of itself. It's not part of another solution. So air is a mixture of nitrogen, oxygen, a little bit of carbon dioxide, a tiny amount of argon, and then really small amounts of things like neon and helium and methane. Nonetheless, this mixture has some major components, it has some permanent components, and it has some variable components. And the major components are nitrogen and oxygen. And if you look at this, you can see the lion's share of all of this is nitrogen, 78%, 21% oxygen. And we don't use nitrogen. It's extraordinarily important to our bodies, it's extraordinarily important to biological processes, but our bodies cannot actually use nitrogen. So most of what we breathe in, we just exhale, and then of course we take in that oxygen and we metabolize it, and through respiration, we then breathe out carbon dioxide. And of course, as you likely very much know from biology, the plants take in the carbon dioxide and they exhale or respire their oxygen. So one of the variable components, and again, looking at these are permanent components, and they are typically unchanged through a fairly deep layer of the atmosphere throughout the world. Our variable components, one of those is going to be water vapor. And when water vapor exists in the air, we refer to it as humidity, and humidity can be expressed in lots of different ways. Oftentimes we use relative humidity, which is a percentage. Sometimes you'll hear meteorologists talking about the dew point, which is more of an exact measurement of the amount of moisture in the air. But when water vapor exists in our mixture, when water vapor exists in this mixture, 78% nitrogen, 21% oxygen, that adds up to about 99%. If you can have up to 4% water vapor, then that's 103%, right? So what does that mean? Well, that means water vapor molecules are replacing some of the molecules in the air. And generally what we see them replacing is nitrogen and oxygen, because those are the most prevalent two gases. And just as a sidebar to that, something you'll learn a little bit later on, H2O, when you look at the actual atomic weight of an H2O molecule, two H's, hydrogen, and one oxygen, is actually lighter than oxygen or nitrogen. And you can see both oxygen and nitrogen are O2 and N2. So they're two together. So two oxygen atoms combining to make an oxygen molecule, two nitrogen atoms combining to make a nitrogen molecule. H2O, three atoms combining to make a water molecule, is lighter than both of these. And so what we'll learn is that humid air is actually lighter than dry air. But nonetheless, water vapor can make up to 4% of the air's volume. And if the Earth had average temperatures that were much, much higher, then you can actually have more water vapor, because the amount of water vapor in any given volume of air is a function of how warm that air is. Where warmer air can hold more water vapor, and that should make sense if you live in Central Florida where it's warm and humid. It's so humid because it's so much warmer. And then colder air holds significantly less water vapor. So what happens if you take very, very warm air that has a whole bunch of water vapor in it and you chill it, you cool that air? Well, that's when you get condensation, and that's how clouds form and ultimately precipitation. By the way, we talk a lot about CO2, carbon dioxide, certainly in the media, almost vilified in the media as a greenhouse gas, something that's helping to warm the climate. But water vapor is also, and is very much a very effective greenhouse gas, perhaps a bit more effective than CO2, and particularly since such large amounts of water vapor exist, it may be a more important greenhouse gas. But nonetheless, water vapor is a greenhouse gas. Aerosols also exist in the atmosphere, but they are tiny solids or liquid particles. So by definition, the atmosphere is a mixture of discrete gases. If aerosols are liquids or solids, they are not part of that mixture. They just happen to be, they're not part of the solution. They just happen to be part of the mixture in there floating around. Water vapor condenses onto these tiny solids. This is very important. You don't really get condensation in the atmosphere in the lowest levels unless there are these particles to get condensed onto. They're referred to as condensation nuclei. So aerosols are very important. They also reflect the sunlight, and they also scatter light. Light waves strike those aerosols and get scattered in different directions. And that scattering is what helps bring us the colors of sunrise and sunset. The ozone layer, instead of O2, as I showed you with oxygen that we breathe in, diatomic oxygen, O3 is what ozone is. And ozone is largely in this layer above the layer that we exist in. So this is not to scale. First off, the atmosphere is an itty-bitty thin layer, like the skin of a peach, as scientists have used that analogy. If the Earth was the size of a peach, the atmosphere would be this. So it's very, 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 very thin. Nonetheless, the ozone layer is well up above the layer that we exist in, where most of our weather occurs. We're going to talk about the layers of the atmosphere in a couple minutes, but we're down here in the troposphere. The ozone is in the stratosphere. And its distribution is not uniform. There's areas where we have a nice solid ozone layer, areas where we don't have a good ozone layer, but ozone is extraordinarily important because it absorbs incoming ultraviolet radiation. So some of that radiation certainly gets to the surface, which is why we wear SPF at the beach, to protect us from the burning rays of the sun, which are UV ultraviolet radiation. It's a shorter wavelength, so it carries more energy. But the ozone layer is up here. And if an ozone layer didn't exist at all on Earth, you likely would have no plants or animals on the surface of the continents, because the ozone layer would be too energetic. And that's why most life started in the oceans, because the water protected us from the ozone. It helped to scatter away the ozone. Very important aspect of understanding weather, climate as well, is this concept of atmospheric pressure. So we talked about the atmosphere being a mixture of discrete gases. Well, each one of those gases is a molecule, and I talked about how oxygen and nitrogen, both diatomic, are actually heavier than a water vapor molecule. So the bottom line is all these molecules have weight, no matter how minuscule. If you add them up, it actually becomes something a bit more significant. So atmospheric pressure, or air pressure, barometric pressure, is nothing more than the weight of air above any level. And so it's not just the weight of air above where you and I are standing down here at the surface, but above any given level, the weight of air above that is atmospheric pressure. So at sea level, right down here where we are at the beach, at sea level, the atmospheric pressure comes in around somewhere between about 14 to, well, it's 14.7 is the exact number we're going to use, pounds per square inch. So for every square inch of Earth, there are 14.7 pounds of atmosphere on top of you. Another way that we express it, we call this barometric pressure. BAR represents bars, barometric. A millibar is just an expression of the weight of air, just the same way as pounds per square inch is, or kilograms would be. But millibars, somewhere around 1,000 millibars is average, that's important, average surface pressure around 1,000 millibars. So if I'm down here at the surface and above my head is 1,000 millibars of air pressure, it's intuitive that if it's 1,000 here at the surface right here, then as you go up, there's going to be fewer of those air molecules above my head. And in fact, as you go up altitude, air pressure does decrease. So you don't have to go very high in altitude for air pressure to decrease significantly. And that's because gravity tends to pull a lot of the air molecules closer to the surface, not stuck to the surface, not stuck to the ground, but pulls them to the surface. So the air has significantly greater density down in the low levels and significantly less density in the upper levels. What happens if you're planning on going hiking up Mount Everest? What are they going to warn you about oxygen here above at the summit? They're going to tell you that the air is thinner up there, right? We've used that term. The air is thinner up there. Well, what does that mean? It simply means there's more molecules down here where we are, where the air pressure is 1,000 millibars, and significantly fewer. As a matter of fact, you can tell that the air pressure is about a third, not exactly, but about a third of the number of molecules in the air on the top of Mount Everest than there are down here at sea level. And so air pressure, extremely important, decreases with height, all right? And it always decreases with height. And air pressure decreases rapidly in the lowest levels of the atmosphere and then doesn't decrease as rapidly way, way up here. But we're talking now 15, 20, 25 miles above the surface. But down where we exist and where almost all the weather occurs, air pressure decreases rapidly with height. The composition of the atmosphere, how we can sort of classify different layers of the atmosphere, we can do it a couple of ways, but we're going to do it most simply using temperature. This is a profile, again, of altitude, just like the previous, with kilometers and miles on this side. So sea level, 10 miles up, 20 miles up, 30 miles up, 50 miles up. Now getting to the outer edges of space, or outer edges of the atmosphere, connecting with space. And then we have temperatures down here, Celsius and Fahrenheit. So, average temperature on Earth is actually somewhere around 59 to 60 degrees Fahrenheit. So this is where we start at the surface. And you also know, as you go up the mountain, as you walk up Mount Everest, you know that the air gets thinner up there. You also know that it gets colder as you go up, right? Well, air temperature generally, not in every single situation, but air temperature generally decreases with height. Okay, it gets cooler as you go up. And in the layer of the atmosphere closest to the surface, and I'm talking about the first 7 to 8 miles above the surface, in the first 10 to 11,000 meters above the surface, that layer in which the air temperature generally gets colder with height, it goes down with height, is known as the troposphere. And that is the layer of the atmosphere, the troposphere, in which 99.9% of all weather occurs. And so this is going to be the area we're going to focus on. Once you get just about to that point, and this level changes in different parts, it actually changes based on the average temperature of this layer, but that level changes up and down a little bit, summer and winter. You get to a point where suddenly the temperature becomes about the same with height, isothermal, it doesn't change, and then it begins to warm up with height. Now, I'm not telling you it's warm, all right? Still 40 below zero, Celsius and Fahrenheit. And even here, we're still at 0 Celsius. At 32 degrees Fahrenheit. So I'm not telling you it gets warm. I'm just saying it gets warmer with height. And this is where all the ozone is. The stratosphere is where all the ozone is. And the reason why it gets warmer with height is because the ozone absorbs those UV rays, and that causes that layer to warm up. Not warm like, oh, how nice and pleasant it is 30 miles up, but it just gets warmer with height. And then we get into the mesosphere, and we know very little about the mesosphere. It's tough to get there, either with a satellite or with a balloon, but the bottom line is we know temperatures drop very rapidly with height there. This is the area of the atmosphere where air pressure increases rapidly enough that as meteors come in, and they tend to burn up. They burn up because the air pressure gets higher. And then you get to this level called the thermosphere. It's called the thermosphere because the UV rays of the sun are completely unblocked. Any molecules they strike, and there's very few molecules up there, it causes those molecules to move very, very quickly, and so the individual speed of the molecule represents the temperature. And so while the actual temperature may be high, there are so few molecules up there, it's a minuscule amount of actual heat. And the aurora borealis happens up there because whatever molecules happen to be up there, they get so excited and vibrate that they glow. Now let me go back to this heat concept. If you took a thimble full of water and you had it at 212 degrees Celsius, so boiling point, and then a bathtub full of water that was at, let's say, 88 degrees, which has more heat? So which could melt more ice? Well, a thimble full of water at 212 degrees could melt some ice that it comes in contact with, but it might be just half of an ice cube, whereas a bathtub at 80 or 90 degrees can melt many, many ice cubes. There's more heat in that gigantic bathtub. So they call this the thermosphere. We say temperatures get very high, but there's no real heat up here. If you were up here floating around in space, you'd not feel those high temperatures because none of those molecules would be in contact with you. Each one of these layers is separated by a boundary in the atmosphere, and it's literally a physical boundary, and it's the pause. And so the troposphere is bounded by the tropopause, the stratosphere is bounded by the stratopause and the mesopause, and there's no upper limit to the thermosphere. And the reason why this happens, this tropopause, tropo literally means to turn. In the troposphere, air goes up, hot air goes up, and cool air comes down. And hot air goes up, and cool air comes down. And in the troposphere, the atmosphere is always overturning and mixing, and that's why it's called the troposphere. It's always overturning and mixing. The air above your head is cooler, right? I'm down here at the surface. The air above my head is cooler. Warm air rises, and then finally it cools and it comes back down. In the stratosphere, temperatures get warmer with height. And so air down here can't go up because the air above it is actually warmer. So in the stratosphere, air sinks and it creates a very layered, that's why they call it stratus, a very layered atmosphere. And so there's an actual physical barrier. I mean, you can't see it, but it's a temperature barrier that keeps air from getting up above the tropopause. And that's what keeps all of the air in the troposphere. That's what it keeps it down here at the surface. So the troposphere is the lowermost layer. Temperature decreases with height. The environmental lapse rate, what is this average change in temperature? So a lapse rate is a change in temperature with height. What is the average lapse rate? Well, it's about 3.5 degrees per 1,000 feet or 6.5 degrees per kilometer. So what that means is that if you're hiking up a 5,000-foot mountain today with your friends, and it is 80 degrees at the surface, you can multiply 5 times 3.5, so that's 17.5 degrees, and you know that once you get to the top of that mountain, the air temperature is going to be 62.5 degrees, because you know that the environmental lapse rate is going to cause the temperature to decrease with height. And again, there's variable thickness as it's in the summertime. The tropopause is warmer because warmer substances expand. In the wintertime, the troposphere is narrower, and that outer boundary is the tropopause. Just a quick example of environmental lapse rates. You can be here down in the tropical regions, down by the sea level, and you have palm trees, and then you can go up the mountain to enough height where it's cold enough to always be snow-capped. So the actual environmental lapse rate changes. That's the average environmental lapse rate. To actually know what the environmental lapse rate is at any given location, you have to measure it. You literally have to measure the temperature. And the way we do that is with the most archaic weather instrument, and that's a weather balloon. This balloon is released, right? And there is a little box hanging underneath it that's called a radiosonde, and it has a thermometer and a hygrometer, which measures relative humidity, and it has a barometer, which measures atmospheric pressure, and then it has a radio instrument that broadcasts, and there's a unit for picking up that broadcast. So as it goes up in the atmosphere, it measures, and it tells us what the actual environmental lapse rate is. And by watching it and seeing how it moves, you get an idea of winds as well. And then when that balloon gets big enough, as it gets higher in the atmosphere and the pressure becomes lower and lower and lower, the pressure inside the balloon causes it to expand, it will pop and this will drop back down to Earth. And you can find these, not often, but they can be found, and you just drop them in a mailbox and they get sent back to the Weather Service. So again, the other layers in the atmosphere I kind of briefly talked about. This goes into more detail about them, and of course you can find this in your book, the stratosphere and the mesosphere, and then your thermosphere up there at the top. So next in this particular chapter, and again, I mentioned this in the introduction, we really are just skimming the surface of meteorology and atmospheric science and atmospheric processes. There's way more to it than what we're going to get into, but we're going to jump very quickly into the Earth-Sun relationship. And there are podcasts in your modules, in your weekly assignments, that go into more detail about the composition of the atmosphere, and in more detail of the structure of the atmosphere, and also in more detail into the Earth-Sun system. But we're just going to run through the Earth-Sun system. The Earth, as you know, is tilted on its axis and it rotates. It takes 24 hours for it to make one complete revolution and a rotation on the axis, and then it also revolves around the sun. So a couple of different motions going on here. One of the most important things, of course, is that the Earth is tilted. Now, why is it tilted on its axis? Almost all of our planets are tilted on their axis to one degree or the other. Most likely, the planet got struck by some large object. As a matter of fact, most scientists have a hypothesis that most scientists are buying into, that shortly after the formation of the Earth, an object that was supposed to be in orbit between Mars and Jupiter got knocked out of orbit by some passing gravitational field and actually struck the Earth and helped to knock it on its side. And then the result of that collision actually resulted in what was left of the Earth, and other material coalesced as the Moon. That's a hypothesis. Almost all the planets are tilted to some degree. Some of the planets are tilted a little bit less. A couple of the planets are tilted way more. One planet's actually way over on its side, almost on its side. And that's all because things struck planets during their formation. Now, that the solar system has been largely cleared of any significant debris, so that really doesn't happen anymore. Passing comets or asteroids potentially can have a catastrophic impact on the globe, but something Mars-sized hitting the Earth does not seem very likely. So if the sun is here, in this case down here the sun's over here, but the sun is here, the sun rays illuminate half the Earth. That's the circle of illumination. The other half is dark, so this is daytime, this is nighttime. And you can see a couple of things here. This is going to be June, so this is summer, right? This is December, so this is the beginning of winter. And in summer, the northern hemisphere is tilted toward the sun, and in winter, the northern hemisphere is tilted away from the sun. We always point to the same point in space. We always point north. It happens to be pointing to the North Star, also known as Polaris. Not a special star, it's just the star we happen to be pointing on. If you begin to study historical geology, you'll learn that the Earth's tilt actually changes. It changes by a couple of degrees back and forth. It also, where we're pointing, changes. Like think of the Earth as a top spinning. Tops precess, meaning they kind of like wobble around. And so we won't always be pointing to the exact same location. The changes in those occur over time spans of 25, 50, and 100,000 years. So that's nothing we're going to feel in our lifetime. But this is where we are today. And because the northern hemisphere leans toward the sun in our summer months and leans away from the sun in our winter months, more direct rays strike the northern hemisphere, and those more direct rays of the sun are the key component to why the summer is warmer than the winter. More direct rays mean more sunlight reaches the surface. In our summertime, it's the northern hemisphere, the southern hemisphere's wintertime. They are tilted away from the sun, and the rays that strike the southern hemisphere are less direct, and so they are in their winter time. So the seasons are the result of the changing sun-Earth angle. So the sun is fixed, the Earth, its tilt is fixed, but because we have this rotation, this revolution, the revolution around the sun, as we orbit the sun, the general relationship of our angle changes. And again, summertime and wintertime, and then halfway around, fall and spring, we're almost straight up and down. So in this situation, the Earth is halfway around its orbit from summer to winter, and the sun's rays are almost equal on the entire side of the planet. On this day, you're going to have 12 hours of daylight and sunlight, and that's somewhere in between summer and winter, or somewhere in between winter and summer. And just a quick note, you can see that in the summertime, the equator has 12 hours of daylight and sunlight, and you see that the number of hours of daylight and sunlight become higher and higher as you go up. And remember, the Arctic Circle, as it's spinning in here, it's always being struck by the rays of the sun, so it always has light. Now, just keep in mind, it's a very, very low angle, so it's a very, very dim light, but it is daylight. And the same thing happens in the Antarctic Circle, because you're behind the Earth. It's sort of blocking, creating a shadow. You have those 6 months of winter. So in our summertime, our days are longer, and then you can see in our wintertime, as you get further and further north, our days get significantly shorter. Here's pretty much another look at that whole thing, but I just want to bring you to down here. Summer, and then winter. In summertime, when you have a direct sun angle, the sun is directly over you, as we see over here in B, and that amount of sun is illuminating that smaller area, so more sunlight arrives in that area, and it just makes a warmer situation. At a greater sun angle, I should really say a lower sun angle, this is 90 degrees, this is at 30 degrees, that those rays of the sun are spread out over a larger area, and there is less heating involved. There's less heating involved. Now, this is at 40 degrees north latitude. In Florida, we're less than 30 degrees north latitude, so this isn't exactly what it's like for us, but the highest sun angle and the longest day is going to be June, around the solstice, and then the lowest sun angle and the lowest and the shortest day is going to be in December, around the solstice. And the equinox is the day that we have an equal amount of day or night. So you can see this path in the summertime is much longer, right? It has to come up here and go all the way around here. So a longer day, and this path is much shorter, and so it's a shorter day. So the seasons are caused by the Earth's orientation to the sun. Again, here is the northern hemisphere's summertime, we're tilted toward the sun, or wintertime, we're tilted away from the sun. And then the two equinoxes, these are solstices, and the two equinoxes is when we're halfway around, and literally half of the Earth from pole to pole is being illuminated. So on this day, the North Pole and South Pole have some very dim daylight and some very dim nighttime. Whereas in the summertime, the North Pole has very dim daylight the entire time, and the South Pole has very dim nighttime the entire time. So the axis is 23.5 degrees. Again, that changes. Also how this precesses changes over time, and even the ecliptical nature of the Earth's orbit changes over about 100,000 year time frames. Not significantly, but just enough. Right now, we're actually closer to the sun. So I want you to think about this. We're actually closest to the sun. You can sort of see the difference between this arrow and this arrow. We're actually closest to the sun, which is known as the perihelion, in it's actually January 4th. I mean, so it's in the wintertime. So that's when we're closest to the sun. So understand that our distance from the sun does not have the primary effect on our seasons. It's the amount of sunlight that strikes the Earth. We talked briefly about the solstices and the equinoxes. And again, they're not always the exact same date. And one of the things I need to point out, it's just like the full moon and the new moon. The solstice happens at an exact moment. There is an exact moment when we're perfectly here, and that is the solstice. So the solstice happens somewhere between the 21st and 22nd, and maybe you've seen in the media where they say, summer starts on, or in this case, winter. Winter starts on December 21st at 12:49 p.m. That is the exact moment that we're at that spot. So the solstices and the equinoxes and even the full moons and new moons and quarter moons, they all happen at an exact moment in time. And so that's why the full moon may actually look full 2 nights, because, over the course of that 2 nights, it looks pretty much full. But the actual full moon is at a very specific time, as are the solstices and the equinoxes. So the summer solstice and the winter solstice, the autumnal equinox is also the fall equinox, and then the spring equinox is sometimes referred to as the vernal equinox. And there are those same relationships we've already talked about a couple of times, and you can get a little bit closer and better look at how that EarthSun relationship works. And again, there's more details on that in the podcast that you can get in your modules or your weekly assignments. Very quickly, big difference between temperature and heat. Heat is synonymous with thermal energy, but heat is the transfer of energy from hot objects to cold objects. Heat is the transfer of energy from hot objects to cold objects. In the simplest terms, temperature is the intensity or the degree of hotness, but in reality, temperature is a measure. It's a measurement. So heat exists. Heat exists in nature. It's energy being transferred. Temperature is a human construct. We've constructed it to tell us something, what the hotness is, the hotness level is. Temperature is a human construct. It is a measurement. All right? And what is it a measurement of? It is a measurement of the average speed of molecules. All molecules move, spin, or vibrate. All molecules. Even your solid desk, which you may think those molecules aren't moving, but they're either vibrating or spinning to some degree. And if an object is very cold, they're not moving very much at all. If that object is very warm, they're moving a great deal. So take a poker that you use to get your fireplace working. It's sitting by the side of the fireplace. It's stone cold. Those molecules are not moving very quickly at all. Stick that poker in the fire for 20 minutes and take it out. Now it's glowing red hot. Those molecules in that poker, it's still a solid, but they are moving much, 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 much more quickly. So the measure of the average molecular motion of matter, with faster molecules indicating higher temperatures and slower molecules indicating lower temperatures. That's what temperature is. It's a measure of the average molecular motion. And again, if you've ever heard of absolute zero, as cold as it can possibly be, well, absolute zero on the Kelvin scale means literally no molecular motion, no motion whatsoever. That's as cold as it can be, and that is absolute zero. So heat is transferred 3 different ways, through conduction, convection, and radiation. And conduction is transfer of heat from molecule to molecule. You literally have one hot molecule touching another hot molecule. And how is heat transferred? Well, the one hot molecule is vibrating more quickly than the other hot molecule. And so if they're in contact, the faster, more rapid vibrations of the hot molecule causes the molecule next to it to begin to move and vibrate more quickly. That causes the molecule next to it to begin to vibrate and move more quickly. And conduction is the transfer of heat through molecular contact, molecule to molecule contact. Convection is mass movement within a substance. So if I put this pot down on the hot stones or the hot coals of the fire, and conduction heats the bottom of the pot, and then conduction heats the very bottom of that layer of water, well, what does the water do when it heats up? All hot substances do what? They expand. That water expands. Now it's taking up more volume, meaning it's less dense, and so it begins to move up by convection. It begins to go up because of a lower density. It becomes buoyant. And then it gets up here to the top of the pot where maybe now it's not exposed to the heat, and it cools off, and it sinks back down. And that is a convection cell, mass movement of a substance. So easy to see in water, but air does the same thing. Air at the surface heats up. When it's in contact with the earth, it expands, becomes less dense, becomes more buoyant, it floats up, and then as it gets up in the atmosphere where temperatures are cooler, it cools back off and it sinks back down. And rising and sinking air really becomes about 95% of all weather, or at least weather forecasting, and that's all happens in the tropopause where air turns over. Now, the last methodology of heat transfer becomes way more complex, and again, we're just going to scratch the surface, and that is radiation. And radiation is the propagation of electromagnetic waves, does not need a medium to move through, meaning the heat from this fire can move through to our hand without a medium. Now, there is a medium in this case, there's air molecules, but let's just assume we're in a vacuum. Even in a vacuum, radiation can move from point A to point B. As you know, the sun's radiation basically travels through a vacuum. The sun is radiating radiation on all different wavelengths, from the shortest, the gamma waves and the X-rays, to short, like ultraviolet, to medium short, we'll call it visible. Infrared starts to be longer, and microwaves and radio waves are actually much longer. And something I want to tell you about the wavelengths, and it's not specifying it here, but we're going to talk a lot about this. The shorter the wavelength, the more energy that wave carries. Gamma rays, X-rays, very, very short wavelengths. Ultraviolet, short wavelengths, they carry way more energy. Infrared, microwaves, and radio waves, very long wavelengths, or longer wavelengths, carry very little energy. That's the reason why you can hold a cell phone with with RF, radio frequency wavelengths emanating from it and moving to it next to your head, because it's very low energy. So it shouldn't do any damage, but the operative word there is shouldn't. Some laws of radiation. Let me just summarize the laws of radiation. Hot objects emit short wavelengths. Cold objects emit long wavelengths. Hot objects emit a great deal of radiation, and cold objects emit very little radiation. And this should make sense to you. The sun is very hot. It emits a tremendous amount of radiation. The radiation of the sun can heat the earth from 93 million miles away. The visible light of the sun can be seen on Pluto many, 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 many millions of miles away, tens of hundreds of, maybe thousands of millions. The bottom line is that the sun is very, very hot, 10,000 degrees or so, and then the radiation that is emitted by it is just a tremendous amount. It's also mainly at short wavelengths, mainly as gamma rays and X-rays and ultraviolet rays. And again, the ozone blocks out the ultraviolet rays, but what arrives at the earth, if you don't use sunscreen, can burn you, because that's how much energy those waves are carrying. Visible light from the violet to the red end of the spectrum, and you can see, looks like a rainbow, because that's what happens to visible light. You break it into its separate colors. It goes from violet, which is a shorter wave, ultraviolet, to red, which is a slightly longer wave. The difference is 0.4 to 0.7 micrometers, right? That's an itty-bitty tiny length. But visible light is in here, and it's actually a fairly short wavelength. Then infrared becomes a longer wavelength. Then you get your microwave and your television and your shortwave radio and AM radio, and these become extraordinarily long wavelengths. So all objects emit and absorb radiant energy. So you and I emit radiation. We emit radiation on the infrared spectrum. It's the heat coming off of our bodies, and it's not a lot of heat, so it's a pretty long wave. We also absorb radiation. Walk outside on a sunny day and put your face to the sun. Close your eyes. What do you feel? You feel the radiant energy of the sun. Well, that radiant energy of the sun left the sun 93 million miles away. It propagated through a medium, and that energy wasn't released until it struck your face and your face absorbed it. And then the energy was released in the way of heat. All right? We all emit and absorb radiation. Hotter objects radiate more energy, as I said, than colder objects, and hotter objects radiate in a short wavelength. The sun sends radiation in a short wavelength. Then the Earth absorbs that radiation, just like your face did, and it warms up. And now it's warm, okay, 59 degrees Fahrenheit. It's not hot like the sun, but it's warm. And so the radiation the Earth emits is in a infrared, longer wavelength. The sun emits shortwave radiation down here, and the Earth emits long-wave radiation. And the really important part about that is when we begin to talk about the greenhouse effect, because the atmosphere is largely transparent to shortwave radiation, meaning the gases of the atmosphere largely allow shortwave radiation to pass right through. But once the sun warms up the Earth, once the sun's radiant energy warms up the Earth then emits away its longer wave radiation, and the gases in the atmosphere, particularly your water vapors and carbon dioxides, they love that long wave radiation, and they absorb it, and they warm up. And not only do the gases absorb it and warm up, but now that they've warmed up, they re-emit more long wave radiation. And those greenhouse gases that readily absorb and emit long wave radiation, they keep the Earth warmer. That's the insulating layer of the Earth. If we didn't have that insulating layer, the Earth would be so cold that liquid water couldn't exist. Without liquid water, none of us would exist. And so greenhouse gases are incredibly important to us. Without them, we wouldn't be here. Why are they vilified in the media? Well, too much of a good thing can be bad. So this slide really tries to summarize some very complex concepts, and a lot of them in as few words as possible. The sun is hot, so it emits most of its radiation at a short wavelength. The atmosphere is largely transparent to that incoming solar radiation. Sometimes I'll refer to that as insolation because it's in a short wavelength. About half of it reaches the Earth, all right? I said this is largely transparent, but some is scattered back into space, reflected, because it hits the air molecules and bounces back, all right? Some is scattered and bounced back from clouds, all right? Some of it is absorbed by clouds, okay? Some of it's reflected back from land and sea surfaces. But about 51% of just pure solar radiation strikes the Earth. The rest, again, reflection, which is known as albedo, scattering, and absorption. There's some absorption. The atmosphere absorbs a little bit. Clouds absorb a whole lot more, but mostly it gets through, all right? The sun emits shortwave radiation. The atmosphere is a window to that shortwave radiation. The Earth absorbs the shortwave radiation and heats up, all right? Heating up, it also heats up the lowest. And when I say the lowest, I mean centimeters of the atmosphere. This is a different part of this. This goes back to convection. Heats up the lowest level of the atmosphere. So how does the rest of the layer that we in warm up? Well, once it heats up that lowest layer of the atmosphere, what does that air do? Warmer substances do what? They expand. It expands, takes up more volume, becomes buoyant, and it goes up. And as it goes up, it gets away from the heat source and cools off. That's our convection. Back to the Earth. It absorbs shortwave radiation, and then it emits long-wave radiation into the atmosphere. Gases in the atmosphere, such as CO2 and H2O, favor the absorption of long-wave radiation, and they heat up. And as I said, not only do those gases heat up, but once they've heated up, they re-emit long-wave radiation back down, around, over, and up to the clouds, to the Earth. And that just creates more long-wave radiation, which creates more heating. So the atmosphere, as thin as it is like a blanket. It's a blanket on the Earth, and that is the greenhouse effect. And it's why we live on Earth. Reiterating the concept of the greenhouse effect, incoming solar radiation, all of the sun's radiation, passes through the atmosphere, and most of it reaches the Earth's surface. And really most of it refers to about 51 to 52%. Some of the radiation may be scattered within the atmosphere. We'll talk about that in a few moments. Some of the radiation may be absorbed by clouds, even some atmospheric gases. And then some of that radiation may be reflected straight back, which refers to an object's albedo, its reflectivity. Some of the radiation is reflected straight back, but the majority of it reaches the Earth's surface. It warms up the Earth. This gray-blue sort of quarter orb here is the Earth. It warms up the Earth's surface. the Earth warms just the very first few centimeters of the air by conduction. That air then warms up and expands and begins to rise, and also heats other parts of the atmosphere through convection. And then lastly, the Earth emits out its thermal heat, its infrared energy, in the form of infrared radiation. Now, some of that infrared radiation does escape to space, but much of it is absorbed by those selective absorbers, those greenhouse gases. Selective absorbers are gases that selectively absorb some types of radiation and not others. And in this case, those gases, water vapor and carbon dioxide, they selectively absorb long-wave radiation, or what we refer to as the Earth's long-wave radiation, terrestrial radiation. Another gas that's a very effective greenhouse gas is methane. Methane largely comes from industrial farms and also from landfills, and although the proportion of methane is extremely small now, as it grows with the growth of industrial farms and landfills, well, then methane's become a more important greenhouse gas, something to consider. But this heating of the greenhouse gases, and not just the heating of the gases themselves, but once they absorb the long-wave radiation, they'll re-radiate out more long-wave radiation, and that creates the greenhouse effect, that thermal blanket on the Earth that keeps our temperature of the Earth warmer than it should be. Our temperature is an average 59 to 60 degrees, and without the greenhouse gas, our temperature of the Earth would be below freezing. So let's look at three different situations. No atmosphere, the atmosphere as we have it, in an atmosphere that we see on a planet like Venus. On the moon, with no atmosphere, all insolation comes through, strikes the moon, warms it up, and all insolation is re-radiated back out to space. And what you end up with is a colder average temperature. In our situation, the incoming solar radiation passes through the atmosphere, warms the Earth re-radiates it out. Some is lost, but a lot of it is re-radiated back toward the Earth, and the atmosphere is kept warm. Again, that 59 to 60 degrees Fahrenheit. But let's consider a planet very similar size to the Earth. They used to consider these planets to be sister planets. Now we know they're much, much different. But Venus, it never cooled enough for its water vapor to turn into liquid water, and so its atmosphere is just full of water vapor and other greenhouse gases. And because of that, virtually all of the outgoing long-wave radiation is absorbed by those greenhouse gases, and the average temperature of Venus is 941 degrees Celsius. So when incoming solar radiation or insolation begins to move through the atmosphere, it can be absorbed, which it is. It's absorbed by clouds. Some is absorbed by even a couple of the atmospheric gases, or it can be scattered, which means just broken up and sent in lots of different directions, or it can be reflected. This is the reflection of insolation, and different objects have different reflectivity, which we refer to as albedo, and the tops of clouds and very fresh snow have very high albedo and reflect back most of the insolation, and then wet roofs and dark roofs and dark asphalt, they absorb a great deal of the incoming solar radiation, and then a light roof is going to reflect a bunch of it out, and that is known as albedo. And this snow at 50 to 90%, fresh snow can reflect back some 90% of all incoming solar radiation, and that's why you get some sunburn when you go snow skiing. It's not windburn, it's actually sunburn, because it's reflecting back off the snow and burning your face. We talked about the absorption of radiation, the reflection of radiation, and some of the incoming solar radiation is scattered. That's simply sunlight striking an air molecule and being scattered in all directions. And the size of the air molecules on Earth are just about the right size to scatter away first, and mainly the blue, and sometimes the greens, but the blue and the green wavelengths of incoming solar radiation. And this is the simple reason why the sky is blue. As the sunlight passes through, the visible light of the sun is white light. It's all colors. But the size of the air molecules favor the scattering of the blues, and that's what makes the sky look blue. Now, if the sun is setting, and therefore it's moving through a deeper layer of the atmosphere, not just straight up and down, but a deeper layer of the atmosphere, or it's rising and moving through a deeper layer of the atmosphere, more and more of the greens, blues, and even yellows are scattered away, and what's left of the light are the oranges and reds. And that's the reason why largely our sunrises and sunsets can be orange or red. So we've mentioned and talked a lot about these greenhouse gases and really try to put a positive spin on them to let us know that they're very, very necessary to keep our temperature above freezing so we have liquid water. But what happens if you have too much CO2? Or this is an 800,000 year history of CO2 in the atmosphere. And of course, there's nobody back here to take these measurements. How do we get this? The cores of ice sheets, such as the Antarctic ice sheet, and cores of sediment, and even cores of pollen deep in lakes can give us a very, very good idea of what the CO2 content of the atmosphere was going back 800,000 years. And these high CO2 levels typically represented interglacials. The low CO2 levels typically represented glacial periods. And then you get up to about 1850 or so, and suddenly CO2 increases dramatically. And this is, of course, after the Industrial Revolution. And it's that rapid increase in CO2 because of the burning of fossil fuels why many scientists believe that human-induced global warming is occurring. And of course, if we warm the globe, what happens? Well, sea levels should rise, and there can be some significant changes, negative changes in weather patterns, as well as gradual overall environmental shifts to a warmer globe, which may not be necessarily supportive of life as we know it. All right, we're going to talk more about climate and climate change coming up. Right now, I want to talk about temperature measurements. And I think you know on the evening news, you're going to get the high temperature of the day and the low temperature of the day. But there's a number of other temperature measurements that can be taken. Mean temperatures, daily ranges, monthly means, monthly ranges, annual means, all different types of temperature data that can be acquired and used. But on a daily basis, we use basically the temperature, whether it's the maximum or the minimum or what's happening right now. And on a weather map, we can use those temperatures to visualize temperature and the temperature gradient to understand how weather is moving. And we do that with a tool we call an isotherm. And an isotherm is a line that connects points that all have the same temperature. Iso is equal, therm is for temperature. And so it's used to examine the distribution of temperatures over large areas. It makes it easy to visualize the temperature gradient. We can also use on a daily basis isobars. And isobars are equal barometric pressure. So they are lines that connect points of the same air pressure, and they make it very easy for us to visualize the distribution of air pressure over large areas. And that's very important because it's a air pressure distribution or pressure gradients that cause the wind to blow. So looking at isotherms and isobars, we can see how the winds are blowing warm air up from the south or cold air down from the north. So these two basic tools of weather are very helpful in seeing how weather is working and how weather is moving. And here are isotherms. This line is the 80-degree isotherm, the 70, the 60. So we can see that there's some cold air that's intruding here and then warm air that's lifting up here. Now this is a different map from a different time, but these are isobars, lines of equal pressure. And you may remember the beginning of the chapter that average surface pressure was around 1,000 millibars. Average surface pressure really is around 1,013, but nonetheless, 1,025 up here in northern Canada, that is an area of high pressure. And then 1,024 is the isobar, and isobars go in 4 millibar increments, so 1,024, then 1,020, and then 1,016, and then you get down to 1,012. And here in the Gulf of Mexico is tropical storm turned into Hurricane Harvey, down at 982 millibars. So we can see a very strong pressure gradient. And here with all those isobars tightly packed, very strong pressure gradient, creating very high winds, which we know is a function of our hurricane. So isobars and isotherms help us to visualize what's happening with the weather. How or why is the weather the way the weather is? What changes the weather? What causes the weather to change and be different from place to place? What are the controls of temperature? Well, any factor that causes temperature to vary is a control of temperature. The number one control of temperature is how much solar radiation is being received at the Earth's surface. Remember, if we're tilted away in the winter, we're receiving less radiation. If we're tilted toward the sun in the summer, we're receiving more radiation. Name a period of time when we receive almost no radiation. Well, how about nighttime? Nighttime, we don't receive any radiation at the Earth's surface, at least where we are, and temperatures drop. In the afternoon, we're receiving the maximum amount of radiation at the surface and temperatures are climbing. So the amount of solar radiation that reaches the Earth's surface is the ultimate control of temperature. Other controls are differential heating of land and water, and this is a big impact on climate. Land heats up more rapidly and cools off more rapidly than water. Land does. Land gets hotter than water, it cools faster than water, and it gets cooler than water. So this differential heating factors of land and water have a big impact on climate and weather. Here's an example. Vancouver, along the Pacific Ocean, and Winnipeg. So Winnipeg and Vancouver are about the same latitude. So you'd think, well, the same distance north, as close to the North Pole, they probably have a similar type of a temperature pattern. But Vancouver is much warmer in the winter, all right, and doesn't get as hot in the summer. The location or the proximity to the Pacific Ocean moderates its temperature. The Pacific Ocean does not cool off as fast in the winter, nor does it heat up as quickly in the summer as the middle of the continent does. And again, Winnipeg cools off significantly in the winter and then warms up very, very rapidly in the summer. And these are your controls. What are your controls of temperature? And this is a function of water and the specific heat of water. And the specific heat is the amount of energy needed to raise the temperature of 1 gram of a substance 1 degree Celsius. And what that tells us is that with water with a high specific heat requires much more heat to raise water 1 degree Celsius or see water lower 1 degree Celsius. And this map here shows us a map of California where we can see the temperatures over land much, much warmer than the temperatures over the water. The land heats up and cools off much more quickly. Other important controls of temperature are altitude, geographic position, cloud cover, and albedo. And again, with altitude, an increase in altitude is very similar to an increase in latitude. You're typically going to have colder conditions as you go higher up in the mountains. The other thing interesting about being higher elevation is that not only will it be colder, but it'll also warm up and cool off more quickly. We talk about this in the desert. The deserts can be very hot and then during the day, but then get very cold very quickly at night. And the reason why is the deserts are very dry and without a lot of water vapor in the air, there are fewer good greenhouse gases, the water vapor, to absorb and re-radiate long-wave radiation. And so at night in the desert with the dry air, the temperatures fall very quickly. The same thing happens in high elevations. There's simply fewer molecules up there. Again, the air is thinner up there, and at a higher elevation, you're going to see not only will the temperatures fall very quickly at night, but they'll warm up quickly during the morning hours, not get hot necessarily, but warm up quickly. Geographic position, again, controls the temperature. If you're long ways from the ocean, you may be much hotter during the summer, much colder during the winter. Cloud cover, very cloudy areas will be cooler, and areas that have high albedo. You just won't have as much of the sunlight strike the Earth's surface and be absorbed if it has high albedo, and it won't be as warm typically in those areas. So the distribution of temperatures using isotherms, this is the northern hemisphere winter and the southern hemisphere summer. So here's the equator, and so we're definitely cooler, right, in the wintertime, and the southern hemisphere is definitely warmer. You can see that warm air goes all the way down into the continent, all the way down to this continent, really heats up in the subcontinent of Australia. You can also see where you have, in the northern hemisphere, temperatures get much colder in the wintertime here, and the very cold temperatures are being pushed down because of the cold air moving to the south. And then you can see the northern hemisphere summer, and here you can see this very warm air is now, instead of being down over South America and down over South Africa, it lifts north up into the northern hemisphere, and you have the very, very chilly conditions there on the way to the north, but very, very warm here over the continent, very, very warm here over the continent as well. Global temperature patterns in the southern hemisphere, because of so much water, you tend to have much straighter isotherms, and they're much stabler. Isotherms do show ocean currents, and on the average temperature range, you have a very small temperature range near the equator, and that temperature range tends to increase with latitude. And as we know, you typically have a greater temperature range. It gets hotter in the summer and colder in the winter, and you have a greater temperature range globally over the continental locations. That was Chapter 11 from Foundations of Earth Science, the 8th edition. a textbook written by Lutgens and Tarbuck and brought to you by Pearson Education. Of course, we talked about the heating of the atmosphere, the composition of the atmosphere, the structure of the atmosphere. Now we're going to begin to move to chapter 12, which focuses on moisture, humidity, cloud formation, and precipitation. And we'll talk about all of that coming up in chapter 12.